So what a digital twin is a combination of three different types of inputs. The first is a comprehensive model of all of your system components. So basically, this is the meters, inverters, and the strings that are on site. So we take, all of the models, all of the orientations for your strings, all of your string lengths, and how they're all connected together, along with real-time meteorological data, so namely temperature and irradiance. And then finally, component performance data. So that could either come from component data sheets or it could come from a third party such as the CEC. And so, like I said, we kind of put these through a series of very complicated mathematical equations and then arrive at the outputs of expected power, but then also expected voltage and current. And again, that's, at the inverter level and at the string level. So the reason why that's super exciting is because a lot of legacy monitoring tools are using linear or a top-down model. You only need really a few details about the site, but then there's a lot less that they can tell you because they don't have the expected voltage and current. First, with a digital twin, the margin of error is a lot smaller. And so you don't necessarily need like a big haircut or an adjustment to solve for all of the unknowns. We think that, linear models can be really good for some of the larger sites. Like if you've got a ground mount that's got all of the same inverter models on site, all of the strings are the same length, there's one orientation, a linear model could work really well for you. But then if you've got a rooftop site, which, I feel like is going to be pretty prominent among a lot of CRE developers, you've got, multiple orientations on a pitched roof. You might have multiple string lengths. You might have different capacities of inverter in the same site. Each addition of heterogeneity is going to introduce, a lot larger margin of error unless you've got a full-scale digital twin that is taking all of those things into account.